Hello everybody. So in this video, we're going to solve some problems on Bernoulli equation, and these are going to be some of the questions that or problems that are in the textbook. I think that they'll be very useful for getting more understanding of the problem of the equation and how to use it in solving problems. So the first problem here is about a this little kid who is holding a water hose that has water flowing, and he places his thumb to cover most of the hose outlet. So as you see here in this zoomed in image. So this causes a thin jet of high speed water to emerge, and this is going upward. And it says here the pressure in the hose just upstream of his thumb is 140 kilopascal. It means that this is the water before it leaves the hose. So the pressure here is 140 kilopascal. And of course it comes out, and as it comes out, it's in atmospheric conditions. So the pressure outside is atmospheric pressure. The hose is held upward, so the water will go up. So the question is, what is the maximum height that the jet could achieve if the velocity of water directly above the hose is 4 meters per second? So we know the velocity here, it is 4 meters per second. We know that it's going upward until it reaches the maximum height. And of course, at the maximum height, the velocity would be zero. Otherwise, it will keep going upward. So the velocity here is known to be 4 meters per second. The velocity here is known to be zero. So we need to know the maximum height that the water will achieve. So to do this, we can apply Bernoulli equation. The conditions apply. We can consider water as incompressible fluid. It's consider this as steady state. There is no pump work. We will ignore the losses. So all the conditions that we mentioned before are valid here. So the question is, what are the 2 points that we are going to apply Bernoulli equation to? So as we said before, we use 2 points that we know information about, and one of them is fully known. In most of the cases, is fully known. We know all the three forms of energy in this point, and the other one is partially known, and we can use this the relation between the 2 points to get the missing information. So we know the pressure here, we know the velocity here. We don't know the height yet. We know here that the velocity will be zero, and we know the pressure is atmospheric pressure at this point, but we don't know the height. So one thing that we need to and about this Bernoulli equation, that we don't need to know the height of the point relative to the water or the ground, or to specific reference point. We can set our reference point based on our information. What I mean that I can consider that point 1 is the reference, so the height here is 0, and then we can calculate the height at point 2 relative to point 1. We will see later if this will make a difference if we take another reference point or not, but this is what we'll do. So given this, we think that you can see that the problem is easy. We know Z1 is 0. We know P1 is 140 kilopascal. The P2 is 1.3 kilopascal, which is atmospheric pressure. We know the velocity here is 4 meters per second. The velocity here is 0. And we know, of course, the density of water is 1000 kilogram per meter cube. So we can now write the Bernoulli equation between these 2 points. And if you write the Bernoulli equation, you can see that we know almost everything except Z2. So this is the missing information. So you can calculate Z2. It's going to be just direct substitution. Just need to make sure that the units are homogeneous. So this has to be in Pascal. So the given information are in kilopascal, so multiply them by 1000. And these are all SI units, so it's going to be fine. And finally, we can find the height to be 4.76 meters. So it's very, very simple and direct solution to the problem. Now let's go back to the point. If I take, let's say, the ground on which this kid is standing on to be the reference, and let's say that the hose opening is 1 meter above the surface of the ground. So what we will do here is that Z1 is going to be 1, and Z2 is going to be 1 plus this height. So you are adding the same value here and here, which will cancel out. So it doesn't matter what is the reference point that you take, as long as it will make it easier for you to do the calculations. So this is a very good point to keep it. Now let's move to the second problem. It is about a large tank that's open to the atmosphere. It's filled with water to the height 5 meter, and there is a tap in the bottom that is open and it's draining water. So we need to calculate the maximum water velocity at the outlet. So again, it's conditions of Bernoulli equation apply to this case, and we need to pick 2 points. So we need 2 points that we know information at. So we know the height here is 5 meters on the surface of the liquid. We know the pressure is atmospheric because it's open to the atmosphere. We don't know the velocity. Of course, the surface will move down as it's draining, so the velocity is not known. We know here that the height will be 0 because it's 5 meters above the hose. So this the velocity, the height here is 0. We know the pressure here also exactly after the outlet is atmospheric pressure, and we don't know the velocity. So this is the missing information. So there is one thing here that is important, a word here. It's saying that the tank is a large tank. This has an important implication on the answer. So when we say a large tank, it means that the diameter is very, very big, so that the when the tank is draining, the surface will move down very, very slowly, because the flow rate draining is divided by this very large area is going to be the velocity, which is a very, very small velocity. So when we have a large tank like this, we can consider, and or let's say there is a river that is a branch is coming out of a river, or something like this. So in this case, we can consider the surface velocity is 0, which is not 100% accurate, but it's very, very close to the real value. It can be 10 power minus 4, 10 power minus 3 meter per second. So 0 is almost the same value. So you can ignore it compared to the rest of the parameters like the pressure and the height. So if you take the reference as the surface, so we know Z1 is 0, Z2 is 5 meters, P1 and P2 are both atmospheric pressure, U1 is 0, and we know the density. So the equation will be very simple. Again, we are applying Bernoulli equation between these 2 points. The pressures will cancel out. U1 is 0, Z2 is 0, so it's going to be U2 square is 2G Z1, and we can calculate U2 directly to be 9.9 meters per second. So this is the second problem. The third problem is an interesting one, because in this problem we are combining things from different chapters. Here we combine chapter 3 and chapter 5. We have a part here that has to do with fluid statics. So it says that water flows through a horizontal pipe at a rate of 0.35 foot cube per second. So this is the volumetric flow rate. And here we'll see that there are some US units, which is a good thing to have as well. The pipe consists of 2 sections. This is a big diameter, which is 4-inch diameter, and a 2-inch diameter on the other side. And the diameter is gradually or smoothly reducing from the 4 to the 2 inches. Pressure difference between the 2 pipes, of course, the velocity here is lower than the velocity here, because the area decreased, so the area will the velocity will increase. So the higher velocity means lower pressure. That's why this U-tube differential manometer here is showing higher pressure on this side than on this side. Okay, this is a mercury manometer, and we are neglecting the frictional effect. We want to find the differential height. What is this difference in height in the mercury manometer between the 2 sections? So this problem is combining the fluid statics, which is this part that takes into account the pressure difference between these 2 points, and combines Bernoulli equation that we can apply to this part of the system. So it's very important, and I said this before, that it's very important to know what equation to use to which part. So in this part, it's totally fluid statics. There is no flow in or out. It's just the surface will move up and down until it reaches the equilibrium point. So once it reaches the equilibrium, there is no flow in and there is no flow out. So it's all what is here is considered static fluid. But what we have in the top is dynamic fluid. So we use Bernoulli equation. So to make it clear, we will apply Bernoulli equation between these 2 points because the pressure here, between the pressure difference between the 2 points is related to the pressure between these 2 points. And we will see how. So here in this, first I'd like to get the data from the problem statement and try to adjust the units and everything that I have. So for we know that Z1 and Z2 are equal. The volumetric flow rate is 0.35 foot cube per second that we can convert into around 0.01 meter cube per second. Of course, there's per second here that I forgot to put. So this is the volumetric flow rate. The first diameter is 4 inch, which by converting the unit will be 0.1016 meters, and the second diameter is 2 inch, which we can convert to meters as well. I'm converting everything to SI units, so you can still solve the problem using American units if you're interested. And now we know the density of mercury. It's not given the problem, but it's known 13,600 kilogram per meter cube, and for water is 1,000. We can use the volumetric flow rate and the area to calculate the velocities in these 2 points, and this is something we will need. So the velocity here and here can be calculated by dividing the volumetric flow rate by the cross-sectional area, which is pi over 4 d square. So we can calculate V1 or U1, which is 1.22 meter per second, and U2, which is 4.89 meter per second. Okay. So now we can start with applying Bernoulli equation between points 1 and 2. We know that the heights are equal. We know the velocities, so we can find the difference in pressure. I don't need the exact value of pressure at point 1 and point 2. All what I need is the difference in pressure. So when we substitute the velocities, the heights will cancel out. The velocities, or the equation will be delta P is rho U2 square minus U1 square over 2. And but of course, this density is the density of the flowing fluid. It's the density of water. It has nothing to do with the mercury. So we know the velocities, we know the density, so we can calculate the difference in pressure, which is 11 kilopascals. Okay. So this is the first part. Now we can use this difference in pressure in the calculations of the U-tube manometer. So for manometer, we can go back to what we said in chapter 3. We will pick 2 points in the same fluid at the same height, at the same connected fluid at the same height, and at these 2 points the pressure is the same. So point 3 and 4 will have the same pressure, and so we can name this height as Z2 and this as Z1, and we are interested in Z2. So this is what we want to calculate. So we can say P at point 3 is P at point 4, and P at unit 3 can be at point 3 can be calculated from P1 plus rho G, Z1 and Z2. And of course, this is the density of water. The pressure at point 4 is pressure at point 2 plus rho water, G, Z1 plus rho mercury, G, Z2. So this is what we are doing here. So this is this equation for P3, and this is the equation for P4. Of course, rho G, rho water G, Z1 here and here is the same, so this will cancel. We can rearrange the equation to have it as P1 minus P2, which is the same P1 minus P2 here. And this is now in terms of the density water, density mercury, G and Z2. So the only unknown parameter here is Z2. So we can substitute in the equation to calculate the value of Z2 and get the height, which is 9.07 centimeters. So this is the last problem that we will solve here. I hope this will give you some better understanding of the equation and how to use it and how to apply it in different cases. In the next video, we will go through some of the applications of Bernoulli equation, which is also a very, very useful thing to know about this equation. So I'll see you next time, inshallah. Goodbye.